Right up until Wi-Fi 6, Wi-Fi itself was always focused on throughput. And I'm not the only one who says that, right? That's what the 11, that 11 standards call themselves, right? So there was high throughput, then they were very high throughput. And even after this, they're going to extremely high throughput. So there's always all about throughput, right? It was only Wi-Fi 6 that was not called that, which is called high efficiency, right? So by itself, you know that there's a difference. And just based on the name. What was the focus of Wi-Fi 6, right? Wi-Fi 6 was completely aimed at making Wi-Fi more efficient in dense networks. So with a lot of users, dense networks, which already just leads you down this path of, okay, I'm going to need to think differently about how I do testing. So that being said, though, there is some modest nod to increase throughput in Wi-Fi 6. There are two new MCS, modulation coding schemes, MCS 10 and 11 over MCS 9 in Wi-Fi 5. So that takes your maximum fire rate from 866 in Wi-Fi 5 to 1200 megabits per second in Wi-Fi 6, roughly a 40% increase. You would expect something like that in terms of an increase in throughput. And we do, in fact, see that. So this is data that we take. The red path here, you see over in the legend, that's Wi-Fi 5 throughput. The horizontal axis is the attenuation, so equivalent to the changing the range, the distance between the access point and the station. And when we look at Wi-Fi 6 versus Wi-Fi 5, that's the difference that we see. I'd just like to actually do a test here and give you guys a little bit of an introduction to the test bed and the UI, because this will be useful. This is kind of the easiest test. So we're using the same test bed. All the tests are done in that same test bed. And in this simple test, what we're going to do is we're going to run traffic from the device under test, which in this case is the PAL 6 as an access point, just to one of the state PALs as a station. And you can see the traffic running through the attenuation, through the splitters here. There's also attenuation on this path, and that allows us to modify the range. Here we go. We start this test. You can see this test. Actually, you're looking at a previous run of it, so hopefully we get equally nice results. And there we go. So you can. This also gives you a sense of the PALs, why people find the PALs a useful testing tool, because in addition to just something like throughput, straight throughput, you get the underlying metrics that let you understand what's going on. So what we're looking at here on the middle, on the right, is the data rate. So that's the fire rate. You can see we're at the 2400 megabit per second fire rate, 2400 megabit per second. So you can already guess the other metrics, right? So we're clearly at MCS 11, as you can see on the top right. We're at 2 streams, you can see on the lower right. We're at 160 megahertz, as you can see on the bottom left. We're 2 streams, so this is a good time to point that out. The state PALs are 2 stream devices. That is, kind of normal for station devices in the Wi-Fi industry anyway, but that is the case. So what we have in there is 16 2-stream devices. And as you watch the test, and I won't go through the whole test, you just saw the data. Anybody who wants to run any of these tests, when we have a break, we can run the whole test. We can do the Wi-Fi 5 and the Wi-Fi 6. I can show you how all that works, but just wanted to give you a sense of how this all works. But you can see the test doing, what we would expect it to do for Wi-Fi 6. And this is the kind of the maximum throughput story. So you can see, by the way, that's the other thing to point out. So with the 2400 megabit per second PHY, you can see we're getting slightly over 2 gigabit per second throughput, which is about what we'd expect to see. This is UDP downlink traffic. So that is kind of the easiest, smallest intro to Wi-Fi 6. That's the easy part. So that's just the MCS throughput enhancement. But as I've said now a few times, really the whole thing about Wi-Fi 6 is multi-user testing. So that kind of basic throughput test, while interesting to see that works, is not really what anybody cares about when they're talking about Wi-Fi 6. what we need to get into now is multi-user testing. So Wi-Fi 6 has two multi-user technologies. One is multi-user MIMO, one is OFDMA. They're both multi-user technologies, but they're different in one important way. Multi-user MIMO actually adds capacity to the system because it essentially creates new independent physical layers by using beamforming. So when you have devices that are spatially separated enough and the AP can figure that out, it can actually point a beam at them and create, a physical layer. And then it can do the same thing to another one and create a separate physical layer. So you actually add capacity. OFDMA doesn't add capacity. OFDMA makes more efficient use of the capacity that it's got on the channel. So the idea there is if you have many, many users and the channel would be inefficiently served by them in Wi-Fi 5, it's possible that Wi-Fi 6, by the use of OFDMA, can make more efficient use of that channel. And we'll definitely talk about that in more detail. So the first one I'm going to do, by the way, is multi-user MIMO, because this is easier to understand. It's not that much really to discuss. And OFDMA is just such a deep pool to get into that we're going to start with multi-user MIMO. If we have a device, an access point serving 3 devices in Wi-Fi 5, anything up, actually anything not using multi-user MIMO, I should mention, just in case anybody doesn't know, that multi-user MIMO exists in Wi-Fi 5 as well. The difference in Wi-Fi 6 is theoretically it can support more users, and also it is defined in 802.11ax in both the uplink and downlink directions. Wi-Fi 6 release 1 still only supports the downlink direction. So that's all we'll talk about today. So when an access point is supporting users not using multi-user MIMO, it has a single channel. It will share that channel among the users, and roughly by dividing it up in time. So everybody gets a piece of the whole channel. Everybody gets a whole channel for some period of time. With multi-user MIMO and beamforming, instead, you actually have multiple separate physical layers. So that each one of those users gets the whole channel all the time. That could be quite a big deal. And it turns out it is quite a big deal in certain cases. Here is an example of some data that we've taken, but you can see if you look on the left, just so you understand what you're about to look at, see on the left, we're doing a 2-user test. So the 2 lines on the bottom left here, the red and the blue line are each of the individual users, and the top line here above them is the aggregate throughput of those 2 guys. That's multi-user MIMO on, and if we shut it off, you can see what happens. But let's do the test. So the way we're going to do that test is like this. So in this case, we actually have, same exact setup. We're picking 2 stations, one connected to the back right set of antennas, and one connected to the front left set of antennas. So as far as the AP is concerned, one of those stay pals is sitting in the back right part of the box, and the other one is sitting in the front left part of the box. And that should allow it to beamform. Some of the useful features of the PALs is how controllable they are. So when you're doing testing, you do have a lot of control. You can kind of really focus in on what it is you want to look at. So what I'm actually bringing up right now is the user interface to our PAL 6. When I look at that, you can see, for example, that I have the ability to turn multi-user MIMO on and off with a simple click of a button. So I knew Prachi had done it for me, but just checking. So there we go. We have a test set up, and maybe I'll just take a few seconds just to give a little bit more explanation of what's going on in this UI. On the last time I talked about the stuff on the right, so you can see roughly it's the same plots. They have many other plots, and you can pick whatever ones you want to see. But on the left-hand side, this is how we set up a test. And what I've set up here is 2 traffic pairs. So you can see the one that's called 5BR, that's PAL number 5 in the back right. And the number that's called 13 is PAL number 13 in the front left. So I set them up. I can configure the kind of traffic I want to run. You can see I'm running UDP traffic between the server and the PAL, meaning it's downlink traffic, which it needs to be for multi-user MIMO testing. So So I have these all ready to go. And what I'm going to do actually is start the test by running traffic to just one of these guys with, again, remember, multi-user MIMO off. So when I run traffic to one guy, you kind of get a sense of what the maximum throughput is on the channel. So you can see we've back to 80 megahertz now. We're 80 megahertz, 2 streams. Well, we're at MCS 10 for some reason. But, anyway, we're in the roughly, 900 megabit per second range. And if I add in the other guy, right? So this is not multi-user MIMO, right? So not multi-user MIMO, you know what's going to happen, right? Both will show up, but they'll share the channel. The aggregate, which now you can see here in blue, is about what one guy had before. And each guy's getting about half. So each one gets half and it's before, right? So now, this is the fun part. We can just make the PAL6 use multi-user MIMO. What you'll see as this happens, this will take just a tiny bit of time, and I'll just walk you through what you're seeing. So the reason the throughput just dropped is that the PAL had to reboot in order to do that, so the connection's lost, there's no traffic flowing. If you look here, we have some nice new tools in the user interface. You can actually see that the PAL6 has gone offline. As it reboots, it just turned green, it's coming back online. These guys have associated. Here they come back. And now what you can see is that each individual user, the red and the green guys, is about where the aggregate was before. And the aggregate is now way up over the phi rate. I mean, this is multi-user MIMO. There's no way to get this, right? The phi rate's actually with interestingly, it came back to MCS 11. So we're back to the 1200 megabit per second phi rate, but there's no way to get what looks like in the neighborhood of 16 or 1700 megabits per second with a 1200 megabit per second phi. So you've got multiple phis running now. And so that's, multi-user MIMO in 11AX. So that's the first multi-user capability. You can also see how that works in the PAL box and with the stay PALs. The harder one from a multi-user point of view is OFDMA. OFDMA, unlike multi-user MIMO, has not been in the Wi-Fi spec before. This is brand new to Wi-Fi 6. It was in cellular specs before. This is like an LTE technology, but it is new to Wi-Fi. The purpose, as I said before, is, and as the name of the spec implies, is to improve the efficiency of Wi-Fi. So why does Wi-Fi's efficiency need to be improved? When you have a lot of users on a network in Wi-Fi, all the devices gain access to the channel by contending for access. They will attempt to put their packets on they'll listen to see whether or not the channel is being used. If it's being used, they will wait. They will send packets. If those packets don't make it through, they will wait longer and try and create an amount of wait time such that random access to the channel won't collide. The probability of collision will be low, right? But the only way to do that is to essentially wait a lot. So the channel becomes inefficiently used for that. So how does OFDMA help this? What OFDMA does, so actually let me take a quick step back. So what that means is that everybody's getting access to the channel. Everybody who wants it gets the channel, and when they get the channel, they get the whole thing all the time. What OFDMA does is allows the access point to essentially break up a single channel into smaller chunks of spectrum and allocate those to the users to use simultaneously. So I think everybody knows that part of the story, that's what OFDMA does. But the interesting part that is maybe not so readily clear is that eliminates the need for contention. And that's kind of the big story with OFDMA, right? So now if you've got an access point with, say, 20 guys talking to it, those 20 guys no longer have to do that whole process of listen and back off and wait and look for collisions and all things like that. They just listen to the access point. So the access point is now completely in control of the channel. It says, you 20 guys or whatever it is, here's your allocation of spectrum, send me your data. And it just keeps doing that over and over again. And it keeps, changing those allocations. We'll get into all that detail. But so roughly that's what's going on. So if you look at this top picture here, right, that's what this is saying. At any given time, user A may transmit and he'll use the whole channel, then user B, then user C, then user D, and he'll transmit using the entire channel, whether he needs it or not, by the way. And in Wi-Fi 6 with OFDMA, at any given time, you may have multiple users transmitting, and they will use only a portion of the channel. And that will happen again and again and again. And by the way, it's much more dynamic than what's shown here. And this is what I was talking about before. It is what that does for you depends a lot on the scenario that you're looking at. So if you're looking at something like devices that are sending a lot of small packets. So for example, the pictures that are shown here were built using 320 byte packets based on a codec of what rate? I don't know. It doesn't matter probably, but 128 kilobit per second codec. So, but a small packet size. So I already mentioned the fact that OFDMA will reduce, will have fewer contentions to gain access to the channel because not everybody is contending now. And the second way that you improve efficiency is by dramatically reducing the amount of overhead that you have, right? If everybody is anybody transmitting a small packet, one guy, if you look here on the first picture, you can see that this kind of brown slice, so this is time on the horizontal axis. You can see that's 363 microseconds corresponding to this 320 byte packet with all of the overhead that goes along with it. And what's shown in this picture is the very, very detailed breakdown of all the overheads, the diffs time, the contention window, various headers, block acts, things like that. So all the overhead is shown. And if you look at the ratio of the overhead to the size of the data packet, the data in that packet is extremely high, right? So what we're showing in the second one down then is if we have 4 users in the OFDMA group, you can see how the ratio now of overhead to data has decreased. What's happened there is that the amount of data being sent is the same. It takes it longer to send because you no longer have access to the full channel, right? Each user in this particular example only now has a quarter of the channel. So his data rate will be slower. So this time will be somewhat longer, but still the ratio now of overhead to data, aggregate data being sent is much lower. And then on the bottom, we're even showing 9 users. And you can imagine this increasing as you add more and more users. So again, efficiency will improve as you have more users on the system, and also you'll see the effect more when you're sending smaller packets. So the testing becomes a very kind of different story for OFDMA. If you have a channel with a few users, if you have a channel with 1 user, OFDMA clearly does nothing at all. If you have just a few users, you can imagine why the benefits would be small. So really testing kind of up until now for Wi-Fi, often people would again just do 1 device, maybe a few devices. When people were doing a lot of devices, it was mostly for just connection capacity on access points, but actually shoving traffic to all of them was not something people really focused on. But so when you're doing those kinds of tests, really what people are looking for is throughput, and other metrics are not really at the forefront. So in the case of large data packets with a few users, OFDMA sort of switches between breaking up users into different frequency bands as opposed to different time slices, but you can see how they might be somewhat of a wash. But when you really make this dense and you make small packets, the difference there, what you're looking at now is not really how much throughput can I get through, but kind of how is that traffic being handled? How well is that traffic flow making it from one end to the other? And there you really want to look at metrics more like delay or jitter, possibly packet loss, things like that. Throughput's really not the metric that you're focused on. So as we just demonstrated, you can really improve the overhead. You can reduce contentions and increase the efficiency. And so there is where you should start to see effects. So when we're doing our testing, what we have been really kind of hammering on from our side and trying to figure out what the correct test beds are and the correct test scenarios are, is trying to figure out kind of what are those configurations where previous versions of Wi-Fi would have been inefficient and Wi-Fi 6 will be more efficient. Do we want to look at throughput? Do we want to look at lost packets? Do we want to look at jitter, latency, whatever? And then there's a lot of different things we have to try and figure out. Is it better to look at uplink traffic, downlink traffic? How many users need to be on the network in order to figure out if OFDMA is doing anything useful? Should the packets be big? Should they be small? There are other things, right? Should we be adding QoS into the mix? So the space of variables that you would need to look at in order to kind of cover all the dimensions becomes quite large. And so this is where, going back to that original slide, I said, with a little heartbeat thing, I said, this is where we're actually now, as we have been able to build up the test beds that allow us to do this testing and the test methodologies that allow us to look at what we want to look at, we're really starting to see, at least, as I said, signs of life. For example, here is a test that we ran with 8 stations. This is uplink UDP traffic with, I think, 166 byte packets. You can see the red curve here is OFDMA off, and the blue one is OFDMA on. And what we're showing here is the CDF of the throughput graph. So just really quickly, the axis on the bottom is throughput. So you can see up on top in the legend, this is throughput in megabits per second. And what each point refers to is essentially how much of the data in your distribution and your measured set of data is below that point, right? So what this is telling us is that by the time we're at about 225 megabits per second, we've seen all of our data. So all of our data is somewhere less than 225. But what's interesting is if you look at the value of 50 in the on the vertical axis, that corresponds to the median of your data. So half of your data is below that and half of your data is above that. And what's interesting is that with OFDMA off, we can see that our median is only about 175, whereas with OFDMA on, we're closer to 200 megabits per second. So we've seen, a fair jump in, the median of our throughput just by turning OFDMA on. And another way of looking at this same data is this one. I really like this view because I also think it tells an interesting story. So that's the same. This is the exact same data. The red stuff is OFDMA on. The blue stuff is OFDMA off. I may have switched the colors, but the labels here are correct. So OFDMA on is red. What you can see for this throughput data, again, this is throughput this is a histogram of throughput. So you can see the throughput values in the horizontal axis. And what you can see is that with OFDMA on, the throughput is a much, much narrower distribution. And with OFDMA off, it's much broader. So what does that tell us? It tells us that OFDMA is doing a much better job of scheduling, right? So the packets are coming through much more regularly. And again, this may not be, the thing that you care about if you're only interested in throughput, if you're only, shoving data down the pipe to send a PowerPoint document or something like that. You may not care exactly when it gets there, but if what you're talking about is getting packets there for some real-time application, gaming or voice or something like that, this is really nice to know that OFDMA is doing a nice job of getting the data through without, bouncing it around and buffering it and then shoving it all through at some other time. So this is also a really nice view. So this is what we mean when we're saying we're seeing signs of life. In certain test scenarios, we really are seeing OFDMA doing some stuff. Our system also lets us run, in addition to throughput, which we generate in our system by using iPerf3, the system also has built-in ability to run ping traffic. And so what you're looking at here is the result of the ping delay for one of those devices in that same exact test I just showed you. Again, this one, OFDMA on in red, OFDMA off in blue. This is latency. CDF, so again, same thing. And what you're seeing here is, if you look, for example, at the 90% latency in this case, you can see that with OFDMA on, we're at 45 milliseconds, whereas OFDMA off, we're way out at 65. And you also, if you look at the far end of the tail, with OFDMA on, we don't see latencies higher than about 60 milliseconds. With OFDMA off, it just continues to tail out here, which again is telling us the same thing, basically that the access point is able to get the devices and get their traffic through on a fairly predictable schedule. And you don't have any devices that, again, just statistically randomly in terms of their access to the channel end up having, very long response times. So again, more signs of life. We can look at jitter as well. So we have multiple stations. We can look at jitter for each station. I picked 4 of them. Red, in this case, red OFDMA on, blue OFDMA off. From a jitter point of view, you can see that the red jitter with OFDMA on remains at a nice low kind of level, sort of bouncing around, somewhere less than a millisecond of latency. Whereas you just get these occasional big spikes with OFDMA off. Again, which makes perfect sense. I mean, if you just think about the fact that the devices are statistically contending for access to the channel, it'll happen, right? It's not something you necessarily would care about if you're not interested in real-time traffic. But if you are, these are the kinds of things that bother you. And you can see OFDMA handling it here. In the previous 2 slides, I had those little green lines showing where stuff was going. So this has 16 stations. So I just got bored of drawing 16 lines. So instead, I just drew big, fat yellow arrows. But that's what that means. So I basically have this access point, the device under test, is now talking to 16 of the 32 stations that I have in here. We're running, again, I mentioned before, these are 2 streams. I'm running 128 byte packets. This is uplink UDP traffic. Let's see, anything else you need to know about this? Oh, so the other thing that I want to show you when we do this test, we're going to start getting into some of the more detailed description of what's happening in OFDMA. We've been talking at the what I like to think of as the end user level, like what do end users care about? They care about throughput, they care about latency and jitter, depending on the application. They care about those things. Those are the things that affect the performance from their point of view of whatever application that they are using. Some of the people in this room, some of the people online will also care about the underlying performance of OFDMA. So by which I mean, in the same way that maybe only end users care about throughput, a lot of developers or other people who are involved deeply in the technology care about MCS or number of streams, that sort of thing. So you need to understand that to understand throughput. With OFDMA, there's some other things you want to look at, like RU allocations and whatever, how many device, what's the percentage of OFDMA traffic versus non-OFDMA traffic, all that stuff. So I want to show you how we get at that. So when I run this test, in addition to running traffic, I'm also going to show you how we can sniff that traffic and how we can start to look at that and start answering that sort of what I call expert level of analysis. All right. So what you're looking at now on the throughput plot is there's these 16 guys down here, a little hard to separate out by eye. The one up here is the aggregate. One of the things that's a little fun with Wi-Fi 6 I found is you can actually see a ramp. You can see the whatchamacallit, the modulation, adaptation, the rate adaptation happening kind of in real time. You can see these guys all struggling their way up towards 1200 megabit per second. They often start quite a bit lower, and you can see it's happening at MCS. The bandwidth is at 80, the streams are at 2. But MCS takes a little bit of time to figure it out, but it eventually does. And so I'm going to take just a little bit of data here, so which we can use afterwards. I'll let this run for maybe 90 seconds. Oh, and we're pinging. Same data as I showed before, or similar to the data I showed before, where we have one of the devices. We have 16 devices sending traffic. One of them is also pinging, and that's what you're seeing here. So there's the ping latency in this plot. All right, so let's stop this. All right, and now I'm going to turn OFDMA on that access point. And so we can run the same data again. We can take a look at it and see what we get this time. But also when I turn OFDMA on, and again, I mentioned before, this is another thing that's just really nice about using the PALs as devices, right? We have, easy control. We can turn OFDMA on and, either uplink or downlink or both with a click of a button. So I will do that, and then I also want to show you how we capture some of that data and we get that deeper look at what's happening when the devices are actually communicating using OFDMA. So this will just take a little bit. You'll see, just like last time, the PAL6 will restart just to take that new setting. And after it restarts, everybody will reassociate. We'll just run that data again. Just in case anybody's interested, this is the setting for the 16 individual traffic pairs. You can see this is UDP traffic with 128 bytes. Packets and other things. So the UI and the API give you full control. In fact, there's many more options. You can configure all of these standard UDP traffic options. And it looks like we're back. Yep, everybody's back now. I'll do this just to make sure that our sniffer is also aware of his job. So by the way, the sniffer, a PAL is a sniffer that you're looking at here. One of the PALs, not one of the state PALs in this case, although we will do that later. Our state PALs can be sniffers. This is actually one of our PAL6s being used as a sniffer. And as a sniffer, you can set it up on any channel, choose any channel width. And you can also tell it to capture only the headers of the packets, or you can get the whole packet. So we'll just be looking at headers for now. So let's get that going. And finally,
is the attenuation static?
In this test, it's static. Yeah, I'm not doing a rate versus range. I mean, you could, but I think it's actually 0. Yeah. Yeah. So you can see somewhere, I guess I don't have it up, the RSSI. As long as you're asking, look at the RSSI. So we're in the mid-neg 30s to mid-neg 40s range on the state PALs. And the difference there is probably just due to the antenna, right? Because they're on different antenna pairs, so they'll be kind of differently pointed at the device under test. All right, I think we are ready to go. So we're going to run this one. This is OFDMA traffic, and you can look by eye at some of that stuff. When I'm saving the data, so we can actually pull it and look at it. Can do a little analysis on it. We'll see if we can see the effect of OFDMA in this particular test or not. But I also do want to grab a little traffic with the sniffer. Yeah. Okay, so there we go. You can see the ramp happening again. Sort of the most fun part. So OFDMA on, remember. And So the way our sniffers are also built into the whole system, you just tell the system which device is acting as a sniffer, and when it sniffs, it will sniff the traffic and it will just pipe that stuff out to wherever you tell it to. I'm having it send it to my laptop. So when I click this, if all is right with the world, it will open up Wireshark, and Wireshark will start. There you go. So Wireshark is now streaming packets, and you can look, for example, for trigger packets. So there's triggers. You can see that OFDMA is working. And if you look at those triggers, you can, well, let me stop this. You know, if you look at, you know, open up any capture, anybody who's looked at OFDMA, you know, captures knows what this looks like, right? If you want to see how OFDMA is allocating RUs, you can look at the trigger frames. You can see that this particular trigger frame contains 4 users. It's users 7, 11, 13, and D. I don't know. I thought that was 13 also, but anyway, I'm not sure. So you can, and then if you were to look in here, you can see the AID that was assigned to this user, and you can see the RU allocation. It's allocation 61s, 242 tones. Unless you have the spec memorized, you don't know what allocation RU 61 means. And that's some of the stuff that we are working on to make a lot easier, and that's what we want to show you next. But let me save this file. All right, so we did that. We took some data. I'm going to stop this one with OFDMA on now, so I can save this away. Let me just get this by again. It looks like maybe my browser is not particularly happy with that, but just like before, I should have it. Yeah, it's here. All right, so this was demo OFDMA on. Okay, so so that's an example of how we can do, you know, these runs. That's 16 stations. Obviously, we have 32 in the test bed. You can, you know, do whatever configurations you like, and that's really, you know, kind of the message we're trying to send here. Which, you know, I think hopefully I've pounded this home, right? Testing for Wi-Fi 6 is quite different. You really do need a test bed that's going to allow you to create these kind of configurations. One of the variables being the number of users that you have. Others, of course, being things like packet size, and you know, and throughput per station. You know, all kinds of variables to mess with to look at OFDMA. So one thing we can do is just kind of, just for the fun of it, since we're all here, we're all friends. Let me look at. These are the 2 guys we just captured. We can see if we actually happen to see any effects from OFDMA in that run. So this is a little prototyping tool that we have, which is part of. Oh, so let me actually use this time while it's importing that data, just to send this message as well. We're working on how to understand how OFDMA is performing, and a lot of visualization techniques, a lot of data analysis. So some of the pictures I showed you before, other visualizations like the ones we're getting to, in terms of RU allocation and whatever percent of packets of different types, those are new, and I think that they're important. But we're actually very interested in kind of partnering with everybody in the room, everybody online, to figure out what are the right visualization tools that will help people, get a good understanding of what's going on. So we can take a quick look at our CDF. Let's just start for the fun of it with aggregate throughput. Not much. And wrong direction. Okay, so this is the kind of thing that we do see. We can see there's an effect there. I mean, something was different when we turned OFDMA on versus OFDMA off, but in this particular test configuration, we didn't see any improvement there. We can take a quick look, at least not in terms of throughput, but as I've said a number of times, throughput may not be the right metric. So we can take a look at, latency based on the ping traffic. Much worse, actually. So that test was quite the opposite set of results than we had seen in some of the previous ones. But like I said, it's an ongoing piece of work for us and others, I think, to figure out what are the right configurations to see where OFDMA is providing benefit. And we have we're definitely seeing OFDMA doing things. I showed you that data before. That's real data that we're able to get. But it's also, this little, analysis here just shows that it's by no means yet a slam dunk to figure out, what the right way is to look at OFDMA. So that's what I call kind of the user level, like I said, of analysis. And what I want to do now is get a little bit deeper into OFDMA at what I was calling the expert level. So RU allocations, et cetera, right? So this, I think, summarizes what I had previously said. When you're looking at something like throughput and prior to Wi-Fi 6, you would look at all the underlying metrics, MCS, bandwidth, number of streams, the PHY rate, and then you would try and understand what's going on, right? But since OFDMA is doing all the stuff that we described before, there's a whole new set of information that you will want to look at. And as I demonstrated just now when I was showing you guys the trigger frame, it can be very, very difficult to get that information out of Wireshark. You can certainly do it, but just opening up one packet as it is, you'd have to read all that stuff and figure out what the heck it means. And that's one packet. And OFDMA is allocating RUs to the users on a packet by packet basis, right? It can be extremely dynamic. So looking at one doesn't tell you anything. Well, it tells you that about that one thing, but it doesn't give you any kind of feeling for what's going on. So question is, how can you get a feeling for what's going on? That's what we want to show you next. And before we do that, we just want to give you, make sure that everybody here and online has a similar understanding of the terminology. So there's a couple of important things. There's resource units, there's AIDs, which are association IDs, and there's tones, right? Those are the things you hear about when you talk about OFDMA. So let's talk about what they are. Resource units are the pieces of the channel that the access point can assign to a user. So you can think of it as an amount of spectrum. You can think of it as an amount of a number of tones, however it is you like to think of it. If you think of an 80 megahertz, well, let's talk about a 20 megahertz channel because that's the picture on the screen. So the picture on the screen here is showing a 20 megahertz channel, and it's showing the possible RUs that can be assigned in that channel. That channel has 242 tones in it. If you assign all of them to a user, that's one RU. You can break those 242 tones up. So you can also assign 106 tones to one user, 106 to another user, or you can assign 52 tones to 4 different users, or you can assign 26 tones to 9 different users. And you can mix and match those, by the way. It doesn't have to be that if it's 26, it's all 26. You can break this up almost any way you want, or the access point can. And so that's what an RU is. When a station associates to the access point, it gets an identification number, the association ID. That's called an AID. So you'll see AID talked about a lot. We'll mention it a lot. you can just think of AID as user in your mind if you want to. So that the AID is the user, the RU, and that's static. So a user gets an AID, it stays that way until he reassociates. But the RUs get assigned to those AIDs, to those users, very dynamically. So that's what that last part says, right? AID number 1, so user number 1 could be assigned 52 tones for a while. Then he could be assigned a different 52 tones, right? Then he could be assigned 106 tones, completely up to the scheduler in the access point. So question is, how can you possibly make sense of that in any sort of reasonable way? One way, and the way that we've gone down, is this way. We can give every one of the AIDs a color. So you can see in the case of, say, 15 users in the channel, we have 15 different colors. Every ID's got a color. And if you look at the bottom of this picture, then we're showing RU allocations. So RU allocations, so on the horizontal axis is frequency. So that whole thing is one channel. That's a 20 megahertz channel. And up the vertical axis is time. So that's saying at one time there were these, at the next time it was those, then those, then those, then those. And if you look at the color for AID1, you can see the access point has assigned AID1 52 tones, then a different 52, then 106, then a different 106. It can even be more complicated than what you're looking at right there. If you do that and you look at all the AIDs simultaneously, so again, this is the same plot now, except no numbers, just colors, so you can kind of watch it as it goes up. You can see how the access point has assigned RUs over time. And that can tell you some things, right? If you look at those carefully, you can see gaps, for example, which would indicate, something, possibly. It's at least useful information to know that the access point has chosen, for whatever reason, at this particular time, not to assign certain AIDs to anybody, right? Is that a scheduling error? Is there a reason for it? But it's the kind of thing that, when you are trying to understand what's going on, it's that, you do want to know about. So it can tell you certain things, but it is a little complicated. Now that you're looking at it, you're basically seeing a bunch of color, and you would then need to make sense of that. I think there's a lot of useful information, but it is complicated, and it is 7 packets long, right? It's 7 trigger frames essentially that are shown there, right? That's still a very small number. We have, however, built that capability, into our toolkit, and in real life, it looks like this. So this is a plot of RU it's exactly the same plot as before. So it's the RU allocations per AID by color, per time. So for packet number on the left-hand side. So you can actually follow this through, and you can see the packet numbers on the left here, right? So that's packet numbers, 200,000, right? So again, you're going to get there's a lot of information that comes out, and that it can help you understand. I'm gonna show you that live, so you can see what that tool looks like if you're actually using it. That was a quick snapshot, just so you can understand. Basically, this picture, that's the idea. This is the reality of that analysis. Another way that you might want to kind of reorient the same data in order to kind of get a sense of what's going on is to say, let me just look at every AID individually, right? So now we've put AID instead of frequency along the horizontal axis. So each AID, we can look at how much of the channel it was actually getting allocated at any given time. So as we go up, we can see what allocation it got. Now, we lose in this picture the actual RU, but we do see how much of the band it was getting. So you can tell if it was getting an allocation at all, and if it was getting an allocation, how much of the band it was getting allocated, right? And that tells you something as well. You can see, for example, that in the middle here where it says reasonable service, you can see that AIDs 5 through 9 are basically getting allocated stuff all the time, roughly, more or less. You can see that AID 10, for whatever reason, never got allocated anything. And that's a very quick view of that. That same information was in the other picture, but it would have been hard to see because you would have had to look for the color for 10 and notice that it wasn't there. That's hard to see. This one kind of highlights very quickly that it's not there. You can see that AIDs 1 through 4 were getting stuff for a while and then all of a sudden stopped. Why? Again, that's the kind of thing you can then dig into. And again, 11 through 15, sort of the same thing. They weren't getting anything and all of a sudden they did. So we have also built in the same kind of, so that kind of rough picture, we have the actual data, and that would look like this when that comes out. So again, it's the same exact thing as you just looked at. So I've actually already imported a PCAF file, but it's exactly like the one that we just saved on the last one. So we can just grab trigger frames out of those and have the tool do trigger frame analysis. So, we're looking now, we've kind of zoomed in on a little portion, maybe the first 700 or so packets. And in the tool itself, you can actually, mouse right over the allocation. You can see that in trigger, this is packet number 483. It's a trigger frame. It allocated AID2 to an 80 megahertz, 996 tone allocation RU1. That's why it goes all the way from left to right on this picture. But here you can see, AID 18 getting the 106 tone allocation RU6. So again, we've kind of done a lot of the work for, instead of having to go and figure out what does RU61 mean, right? We did this mapping and we're showing it graphically like this. So you can see what things look like. And so, and in addition, so this is what I was saying before, right? We were looking before at like 7 packets, whatever. So this is 10,000 packets, right? So that's why these things can become pretty complicated. With the tool itself, you do have more control. So, obviously you have the hover capability, and you can also, remember I was saying before, well, it would be difficult for you to follow around, or see that 10 didn't have any allocations, or something like that. The tool will also allow you to pick an AID to follow. So if you just want to see how AID 1 is getting assigned, that you can just look at that. So this actually is a little bit easier view, right? And then you can switch over and look at other AIDs. So this gives you kind of a sense of how the how the access point has decided to allocate bandwidth to the devices. And let's see, there's a couple other. So the other view that I had mentioned before, what you'll see here as I scroll through this, I'm not going to go through everything. Anybody interested, I just want to, I'll say it again at the end of the day. We're very interested in working, very closely with anybody who's interested in this, and making sure that we build the visualization capability, analysis capability that will help people do their work, right? I mean, as the testing people, we just want to, make it as easy as possible. So there's a lot of views here. I won't explain all of them. That's one of my particular favorites, but this is the one that I showed in the slides before. So you can see, with 16 guys, you can get a nice visual sense of who's getting allocations and who's not. You can notice, for example, that RU4, there's actually nothing here on RU4. Now, again, remember, the reason for that is probably because we have so many stations associated and we only ran traffic to 16, that there was probably somebody associated who got an AID who doesn't get any allocations. But you can see, you can kind of follow this through, see what's going on. You can also look at specific packets and see what they look like in terms of, let me find something interesting here. This won't be that interesting, but let's see, this is packet 9912. Let me see if I can grab that packet. Packet 9912. Okay, so here's packet 9912. And what this gives you is the ability to just look at any given trigger frame and kind of get a nice kind of visual understanding of what actually went on there. So 9912 is a trigger. It had 8 users in the trigger. You can see along this axis what the RU allocations are, where they actually are and, how wide they are. So this is subcarrier. So it's actually telling you can hover over it. It'll tell you that this is, RU allocation, RU1 of the 242 tone allocations. That went to AID1, et cetera. You can do that for all of them. The vertical axis here is actually telling you what the uplink target RSSI is for each of these things. One of the things about OFDMA is that since the users are responding simultaneously, the AP also requests certain power control capabilities. So it asks the APs, it tells the APs what uplink RSSI it wants to receive its signals at. And so that's what's plotted here. So you can actually see, instead again of opening up every one of those things in a trigger frame and trying to figure it out, it lets you see that. And the reason I chose this one is that we also have, analysis where we look at those uplink target RSSIs and we look at the differences between them and we highlight when they're very different, because we think that's also kind of an interesting thing. So you can see that for whatever reason, this guy is, the request is negative 63 dBm and the request on this one is negative 53. So there's a 10 dB difference between what the AP is requesting from this one and what it's requesting from that one. So, for whatever reason. So these are the kind of tools that we're building to really give kind of a nice next level understanding of how OFDMA is working and kind of what's going on. There's a lot of other views. Oh, here's an interesting view. So this one actually looks at all the trigger frames and it tells you how many how many users were in the trigger. So you can see that for this particular set of data, most of the time, slightly over 50% of the time, the triggers had only one user in them. And then, this is 7 users in them. So, it was 7 users. That's sort of weird. Oh, it's very few. It's this little skinny guy, right? Only 1% of the time does it have 7 users in it, and then et cetera, et cetera. 8 users is this one, right? So 8 users is 7% of the time. So kind of breaking it down that way. So this gives you another, view into how is the AP scheduling? What is it decided to do? You can see that here it's all, it's decided to give mostly the whole channel to one guy most of the time. This is the same information, but again, looked at another way. This is just a histogram of the RU allocations themselves. So all the unique RU allocations that are seen are written here on the bottom. And so, for example, that first big bar on the left, that's the 996 tone RU1. So most of the time, that's what's being allocated. It's the same view, but just another way of looking at the information. And again, it breaks out a little bit more. So you can see all the different 242 tone RUs, this one, and this one. So there's a bunch of those. You can see how often it's allocating 20 or 40, whatever. So lots of different ways. And this is the kind of thing that, we're finding useful in understanding how the devices are behaving. And we're hoping, that others will find useful as well. So I think I know lunch is at here and I'm just about at the end. So I'm going to show you a last demo. Here's another thing that's tricky about OFDMA testing that wasn't true before. So we've done a lot of sniffing. I just showed you sniffing and then analysis of trigger frames, right? Trigger frames are management frames. Anybody can see them. But actual OFDMA packets, so what are known as HEMU packets in the downlink and HE-trig packets, so responses to HE to triggers in the uplink, those packets, those can't be picked up by regular sniffers. Regular sniffer won't see them. They're coming on a specific RU allocated to a specific AID, and a regular sniffer won't see them. So it is possible, however, to see them. But as far as we are aware at the moment, the only way to do that is to have a dedicated sniffer that you tell what the AID is that you want it to shadow. So we keep telling you that there's 16 stay pals in this thing, and we haven't really given you some of the underlying rationale. So let me do that now. If you want to actually see all of the traffic that's going on in the network, like all of it, right? You know, the data packets, going to each of the users. The only way to do that, and let's say you have 8 users on your link, you would actually, and they're all doing OFDMA, you would actually need a sniffer to be looking at each one of those users, one at AID 1, one at AID 2, etc. So our 16 stations, if you look at the way they are, the way they're set up here, you can see there's sort of 4 groups of 4. Don't worry about the left and the right, because that's 2 different boxes. So let's just pick one of these. So actually, I guess it's on the left, right? So we have 4 groups of 4, and you can see one has a W, win, says win, and the other one says lin. So our stay pals actually come in 2 flavors. One is a Windows version and one is a Linux version. There's a couple reasons for this, but I'll give you maybe the main reason, which is that we've had a lot of feedback from customers that they like the idea of being able to test against stations that are representative of devices that are out there in the real world. So this is using a Linux Ubuntu, OS. So it's Chromebook, whatever, and the other one is Windows 10, I think, something like that. So it's the OS that's out there in the world. So we have a Windows and a Linux. So you can have one station on Windows, one on Linux, and we have 2 more in there. Now those other 2 could be stations, but because they're Linux devices, they can also be sniffers. And the idea is that you can then have one station sniffing, let's say, your Linux traffic endpoint, and one stay pal sniffing your Windows traffic endpoint. So essentially, you'd have 4 simultaneous traffic endpoints. 8 traffic endpoints, 4 Windows, 4 Linux, and you would have 8 sniffers looking at each of those. So that is a complicated mess. And you would end up with all kinds of sniffing stuff. And that brings us to a capability that we've actually had for a while in our testbed. And it was not invented for this reason, but it turns out to be incredibly useful for this reason, which is something we call synchro sniffing. It's a synchronized sniffing capability. And what that allows us to do is to sniff simultaneously at multiple points in the system, and to use a combination of NTP and PTP, I think PTP mostly in this case, to time align those traces and put them all into a single PCAP file tagged by which sniffer you would actually pick up the data. So at the end, you don't have 8 traces that you have to kind of compare. You have 1 trace, all the packets time aligned, you know which sniffer they came from, and you can then analyze that. So, and with that, then we can look not only at, say, the trigger frames, but we can actually look at the underlying HEMU and HETrig frames. So that's what I want to show you a demo of. I'm going to show you a demo of us doing that sniffing. So you can see now the data coming in, and you can see the probe IDs. So remember I told you 4, 7, 12, and 13 or something, and you can see the probe ID coming in there. In this field, says Synchro Sniffer Probe ID, and you can see all that data, all those packets coming in. When we assign the AID to a specific sniffer, it will pick up the traffic from that AID, including HEMU and HETrig packets, and then they will show up in here, and we'll have one big combined happy PCAP file. And when we do that, that lets me shut this off now. So then we can start looking at this kind of data, right? So then we can start giving, for example, statistics on how much of the traffic, is HESU packets or not HE packets or HETrig packets or HEMU, that sort of thing. and our kind of traditional set of statistics like RSSI or MCS or number of streams or whatever it is, we now can basically add another dimension to those. So we can look here. So these would be RSSI for the uplink HE trig packets, for example. We can do the same thing for the HEMU packets in the downlink. We can look at MCS, RSSI, other things like that. And we do that by setting some of our state pals as sniffers and assigning them to be the AIDs that are in the traffic flow.